This is a video for MEI Core Pure Mathematics, complex number 6, exponential form, 6.4, using the exponential forms of sine theta and cos theta. We've already seen expressions for cos theta and for sine theta in terms of e to the I theta, and we saw these derived in a previous video. Let's take that a little bit further. So if we let z equal e to the I theta, I could rewrite this expression up here as cos theta is equal to z plus z to the minus 1 over 2. And this leads to an expression for cos n theta being z to the n plus z to the minus n over 2. Now this is not obvious at first glance, so let's just have a look at that. If I have a look at z to the n, that's really e to the I n theta. And z to the minus n is e to the minus I n theta. So if we have a look at the whole lot over 2, then this thing is cos n theta plus I sine n theta plus cos n theta minus I sine n theta, and the whole lot is over 2. Well, these two bits cancel, the I sine n theta and the minus I sine n theta, so this really does give me cos n theta. And similar piece of working will give you this expression for sine n theta. And you might like to just trace that one through for yourself to make sure that you can make it work out. Again, notice we've got a 2i on the bottom. Now these results are very useful for expressing either powers of cos theta and sine theta in terms of multiple angles, or vice versa, multiple angles in terms of powers. And both of those can be very useful for integration. Okay, so let's have a look at this example integral. I'm trying to integrate sine to the power 4 theta, and the suggestion is that we express sine to the power 4 theta in terms of multiple angles first of all. So let's have a look at sine to the power 4 theta. That's going to be z minus z to the minus 1 all over 2i to the power 4. And that's going to be equal to 1 over 2i to the power 4 times, we're going to multiply out this bracket now. I'm going to get a z to the 4. I'm going to get plus 4 lots of z cubed times minus z to the minus 1, plus 6 lots of z squared times minus z to the minus 1 squared, plus 4 lots of z times minus z to the minus 1 cubed, plus minus z to the minus 1 to the power 4. And now if I just expand some of that, I'm going to get equals 1 over 16 times z to the 4 minus 4z squared plus 6 minus 4z to the minus 2 plus z to the minus 4. And rewriting these, putting the powers of 4 and powers of 2 together, I'm going to get that is 1 over 16 times z to the 4 plus z to the minus 4 minus 4 lots of z squared plus z to the minus 2 plus 6. Now this thing here is just 2 cos 4 theta, and this thing here is just 2 cos 2 theta. So sine to the power 4 becomes 1 over 16 times 2 cos 4 theta minus 8 cos 2 theta plus 6. And so my integral of sine to the power 4 theta d theta is just the integral of this thing. Well, notice I can cancel a 2 out of all of this, so it's actually going to be 1/8 of the integral of cos 4 theta minus 4 cos 2 theta plus 3. Now when I integrate cos 4 theta, I get sine 4 theta over 4, so I get 1 over 32 sine 4 theta, and then I get from the integral of cos 2 theta, I get sine 2 theta over 2, so I get minus 1 over 4 sine 2 theta plus 3 theta over 8 plus a constant. Okay, there's all of that worked out much more neatly for you. This is our derivation of sine to the power 4 theta and confirmation of this result here. And then finally using that in the integral to end up with this result here. The next and final video in this sequence is 6.5 summing series using de Moivre's theorem.